Hello, it's Keith here. This is lesson 6 of my multi-platform Z80 tutorials. Now, sorry for the non-Amstrad people, but this is going to be a quite Amstrad specific lesson, but it's going to teach some really good stuff, so please bear with me. And the Amstrad users, you should really enjoy today's lesson, because we're going to teach you how to write your own sprite grabber and sprite putter, sprite displayer, that you can call from basic. So you can write a simple little basic program to handle your key input, and then you can use a faster assembly language to show sprites on screen. Now, this isn't the fastest way of showing sprites. It's a relatively simple one still, but I think it's a good level for the stage we're at in these tutorials, and it is good enough that I think you can have some fun with it and make some nice little things of your own with it. So let's make a start and let's have a look at what we're going to create today. So we're going to show our assembler as always. And let's get that in frame here. And we'll create a new program. So first thing we're going to learn about today is something known as a jump block. Now, when you're writing a program, you will get to a point where you want to split your program out into multiple sections, and each section will be in a different program and will be loaded into memory in separate places. And the way you allow yourself the flexibility to code in an efficient way, but still have places that you know where to call, to jump to get the commands you want, is you create something called a jump block in a specific known location. And this is how my Chibiakumas game works. The core, which is the main module of the game, has a jump block which all the other functions, all the other subprograms call to call the commands that software does provide. I'll just show you that now. You might as well have a look at that. Just a moment. And here is the start of the jump block. So you can see these are all the commands that the core provides that the levels and the menus will call, and they all have a specific location. But ours is going to be much, much simpler than that. I just wanted to show you it was something I used. So our program's going to start at 8,000. There we go. And then we're going to define 4 commands today, but we'll start with just 3 of them. So jp get and jp put sprite, and then jp get mem pos. Unfortunately, today's example is going to be quite long, and because the different modules can't really work without each other, we're going to have to do all the coding up front, and then we'll see it working at the end, which I know will be a little bit frustrating, but it's not very easy to show these examples without either writing more unused code just to show the examples working earlier on, or just getting it all done in one go. So we're going to get it all done in one go. Now, the first thing we're going to do is we're going to tell our software we want to capture a sprite from this area of the screen, and what we need to do is need to convert an area of the screen to a screen memory position, and we're going to do that with a command called get screen pos, which we're going to define now. And the first thing we're going to do is we're going to pass this command bc, and bc is going to be x and y of the screen. And we're going to measure in screen bytes. So the Amstrad CPC on mode 1 is 320 pixels across, 4 pixels per byte. So it's going to be 80 bytes wide. Now this is, it's kind of a necessary simplification because working at the pixel level is quite complex. So working at the byte level is really the only viable option if you want speed and simplicity. And we definitely want simplicity today because this is a beginner's tutorial. So first thing we're going to do is going to back up BC. And then we're going to set B to 0, and that's because we need to look at Y first. And then we're going to load into HL something called scr address table, and this is the screen address table. So let's leave that alone for a moment, and let's define the screen address table. And well, what is it? Well, I've actually lifted it straight out of my Chibiakumas game, and I think I actually borrowed that from an Amstrad CPC, an Amstrad action example or something. It's a kind of default thing, and we're not going to type it. We're going to cheat. We're going to copy paste it straight off my website, and I suggest you do the same. Do not try and type this. It's just not worth it. There's nothing to learn. It's always the same. at least for this screen configuration, which is the default screen configuration. If you change the size of the screen, for example, you can reconfigure the Amstrad screen to be more like a Spectrum screen. Well, if you do that, this table would need to be changed. So we're just pasting that in, and this contains it's 16-bit, so each screen memory location is a 16-bit, is a 2-byte definition. So these 2 bytes are the first line of the screen, these 2 bytes are the second line of the screen, and so on and so forth to the last line of the screen, the 200th line here. And so 3F80 is the offset of the last line of the screen. Now, as I said, I copied this straight off Chibiakumas. Chibiakumas actually works with 2 screen buffers, so this is defined from 0. So we actually need to add the base of our screen memory to the memory addresses in this table before we've got the true memory location. So we'll do that in a second. If you don't understand what that means, just ignore it for now. Just copy what's on here and it will work. So we need to do that. Now, BC currently contains 0 in B, and the C contains the Y screen address. Now, as I said, there's 2 bytes for every Y location here. So we need to add BC to HL, but we need to do it twice because we need 2 lines, because we need 2 bytes per line. So that's why we're doing that. And now HL will point to the correct screen address for the line that we wanted to select. So what we do is we load A, HL. So we're loading the first byte into A, and then we'll do a rather odd thing. We inc HL, and then we do load L, H, HL. And then we do load L, A. Now, we're loading L with the value we just selected here, but this line might look a little bit odd. We're loading into H from memory address in HL, and that kind of looks like a bit of a paradox because you can't load H from HL when HL is the address and H is the destination. But it does work. The way the Z80 works at that sort of hardware level, I guess, is the data comes out of HL and then it's stored in H overwriting H, but it doesn't happen instantaneously. So HL is still valid at the point where you're loading it from. Of course, you can't do this because that will corrupt HL, and then HL will be corrupted at this point. So that's why we're using A here. Now this is a great point for me to show another really excellent command that you will want to know about, and the command is called the align command. So when you're working with compiled code, sometimes you want to be able to make assumptions about where in the final memory that compiled code occurs. And what you can do is you can do this align command, and that will tell the system, I want this data to be aligned to a certain byte boundary. Well, what does that mean? Well, let's just have a very quick look and we'll just see. Let's have a look at this little sample program here then. So we've got a few bytes here, so if we compile this, compiled fine. And let's just go to our debugger and pause. And what we're going to do is we're going to have a look at the actual memory address where those bytes compiled to. So you can see we've got some junk here, but we can just ignore that. So you can see the 2 here and the 3 ones. And if you look at our source code, we didn't say anything else. But well, what if we want to actually have that 2 in a very specific position? Now, what if we wanted to have it at the start of this line here? Well, you could do that just by putting another origin command in, and that will work in some cases, but sometimes you need to know a certain piece of data will be in a certain kind of position, but using lots of origin commands is going to be very restrictive on your code. It's going to waste a lot of memory, and well, if you put something at 8100 and then this piece of code suddenly gets larger, well, maybe it's too large and it no longer fits, and it actually overlaps 8100. So the far easier thing to do is to use a command called align. And what this says to the assembler is, hey, I need this code to be in a certain position because I'm going to use this code in a way that will only work if it's in that position. And so if we put in a line 16, what this will do is this will align to a 16-byte boundary. And we'll have a look what that means. Sorry, just a bit of a weird pause there. So you can see here's our 111 as we had before, but now our 2 is at the next 16-byte boundary here, and it's been padded out with a bunch of zeros. Okay, well that's what's happened there, but let's have another look here. So suppose this was now 111333, and we'll assemble that. Well, you can see this is the same, this is in the same position, and there were fewer zeros. So a line has shifted this to the point where it's now on a 16-byte boundary. Well, what if it was a 32-byte boundary? Well, you can now see it's at 20, because that's the first 32-byte boundary that was available. And one thing you may want to do from time to time is do a 256-byte boundary, which obviously will use a lot of memory, but you may need to in some cases. Well, here's our 1s and our 3s, and now the 2 is at 8100. So we've put it on its own byte boundary, and this is quite clever because you can define H as something specific like the 81, and then use L, and you can set L to other things, and this is quite often used in for lookup tables for bytes. If you want to quickly mask a sprite so that you can keep the background transparent, you need to have a mask to use with your AND command, and what some games do is they use a 256-byte mask table so that they can quickly look up the byte they want to put to the screen by setting L to that byte, look up the appropriate mask for that byte in a lookup table, and then off they go. I know that sounds a bit confusing, so if you don't understand it, just forget about it for now. This all starts to become much clearer as you start using these commands yourself, so just don't worry about it. I just wanted to explain it. So anyway, let's go back to our 16-byte boundary for our last example of this. Now, if you remember, sorry, here's the 2 that we've just compiled. That's the old one down there. So you remember this is at 10 here. But then, well, what if this gets a lot bigger? Well, you can now see it's at 20 and the zeros are here. So what does it mean? Well, the align command guarantees us that our data following the align command will be in a position on the boundary we specified, but it doesn't guarantee which one. So it allows us to make some assumptions without wasting all of the memory we would if we used an align command. And it also allows our code to grow, so we don't have to make our origin command would restrict us to a specific position in memory, and if the code before that grew to the point where we had overpassed that position, we'd be in trouble. Whereas the align command just says, well, hey, I need this next code to be at a certain relative position, but I don't care where. So it gives us some flexibility, but it gives us some ability because of those assumptions. So let's get back to our code. Well, what are we using it for today? Well, all we're saying is, well, these 2 bytes need to be aligned on a 2-byte boundary. And what does that allow us to do? Well, quite simply, it allows us to take this IncHL and change it to an IncL, because we know that that second byte will not be at the end of a 256-byte boundary. So what does that mean? Well, if you look here, if the first byte was here and the second byte was here, then H would have to change from 7F to 80. But if we know that won't happen, if both bytes are, say, here, well, 7F can't change, so we only need to change L. We only need to IncL. And IncL takes 4 ticks, and IncHL takes 6. So by using that align command, we've reduced the amount of ticks we need to use by 2, and all we've potentially lost is 1 byte of memory. Now, it's not a great saving in this case because we won't use many screen lookups, but it's a good example of the kind of time you can use an align command to squeeze a little bit of extra power out of the system by making those kind of assumptions. And as I said, with regards to lookup tables, sometimes you want to do more advanced things using bigger aligns so that you can use numbers from 0 to 16, and you can align on a 16 boundary and then add to your address to use it as a lookup. There's a lot of things you will want to do there, and as I say, they won't be clear to you today, but as you start coding your own stuff and thinking, hey, I need to do things, I need to do this, how can I do it, you'll suddenly start to realize lookup tables and aligned memory will allow you to make savings and to allow you to do things more quickly than you would be able to otherwise. So it's something you definitely want to know about. So anyway, back to our code after that rather long distraction. So pop BC here. This gets back our x and y coordinates, and this time we're going to load C with B, so we're loading C with our x coordinate, and we're loading B with C0. Why are we doing that? Well, you remember I said before that the screen address table in this example does not have the base memory of the screen actually in it. It starts from 0. Now our screen base memory is C000, so by loading B with C0 we are applying the base screen memory to the addresses, and it will now contain the correct base address. And because we're adding the X position, which is already in bytes, we now contain, when we do our add HL, command, HL will now contain the correct screen position for not just the line but also the X coordinate, and then we just return. So if your screen memory was at a different position, for example, if you'd relocated it to 4000, which a lot of people do, for screen buffers, you would change it to a 4 and it will work the same. And that's why I've done this screen table in this way, because it is a more flexible screen table. So we now know the first line of our sprite for the screen, but the Amstrad CPC, the ZX Spectrum, a lot of systems have trouble with the next line is not directly below the last one in the memory. So we have to calculate the next line from the original one, and it's a little bit tricky. So this is what we do on the Amstrad CPC. So here's our next line command, and what we do is we load A with H, we do add load H with A. Now why we do this is each line is and 800 below the last one, because it's 800. We don't need to mess with L because it won't change. So we save again a little bit of memory, a little bit of power, sorry, by just changing H in this way. But unfortunately, it's not just that, because as I say, each line is if we just add 800, we're going down the screen one line, but when we get to the bottom of the memory at FFFF, we will actually go back to 0. The screen doesn't work like that. It rolls back to CO50. So we need to check if that has happened, and we need to correct for it. So what I do, because you will see other examples that work differently, I check bit 7 of H, and if it's not 0, we return. If it's not 0, we return. Now the reason I do that is if bit 7 has gone to 0, then we've cycled over from FFFF to 0, something's gone wrong, we need to fix it. You will see other ones that use, I think they use if the carry bit's set. The reason I don't do that is because this version works quite nicely with regards to if you've modified the screen base to 8 or 4, as I do, 8000 or 4000 like I do in Chibiakumas. I use self-modifying code to reprogram this, and this is more easily reprogrammable for other screen bases than the carry version, which wouldn't work for other screen bases. So if we've got here, we need to reset our screen, and the way we do that is we load BC with and CO50, and then we do add HL, BC, and then we return. Now, whatever's happened with the Amstrad CPC screen, we are now in the correct position for the next line, just with a bit of legwork to get the correct screen address. So we're now sorted. So that allows us to get the screen position of our sprite and to move down the sprite to the next line. So we made a decent start there, but unfortunately we do have a lot more code to write. So let's get on with it. So this is going to be our get sprite command. And our get sprite command is going to take 5 variables. We're going to run this from basic. Let's just paste in. I've written some documentation. As always, all of this is available on my website. I know this is a ridiculously large example, but it was what I wanted to show, and it shows a lot of good stuff. So we have to type the code if we want the result, and the result is quite nice today. So we're expecting 5 variables from basic, and if we haven't got them, we're just going to return, because otherwise we will make a mess. And the first one is the destination in memory where we're going to save the sprite. So what we're going to do is we're going to load E with ix plus 8 and load D with ix plus 9. And let me explain that. Well, the parameters come in backwards. So this will be the first one, this will be the second, this will be the third, this will be the fourth, and this will be the fifth. But they're all 16 bits, so you have to sort of double that up. So this will use 0 and plus 1. This will use plus 2 and plus 3, blah, blah, blah. Now, little endian, so that means we load in the low value, the low value byte first, and then the high value byte, which is why we're doing it in this order. So that is the destination where we're going to save the sprite. And then what we need to load next is we need to load B from ix plus 6 and load C from ix plus 4. Now why have we skipped number 5 here? Well, these are only 8-bit bytes. We're only expecting values from 0 to 200 for our width, for our height, and 0 to 80 for our width. Basic always passes 16-bit values, so we're just skipping one because we're not expecting it to be needed, and even if the user had filled it in, we couldn't do anything useful with it. So we're just going to skip those. And then what we're going to do is we're going to load A from ix plus 2. And what are we going to do with A? Well, we're going to do something quite interesting with it. We're going to load IYL with A. IYH with A, sorry. Well, what's IYH? Well, we haven't mentioned that before, have we? And there's a good reason we haven't mentioned it. Let's just pause our assembly here and have a look at the Z80. Now, these are the registers that the Z80 offers to us, and you're probably thinking, well, what's this IYL? What is it? Where did it come from? Well, when the Z80 was sort of originally designed and documented, the Zlog, when they invented it, they gave the documentation of all of the A, the HL, the B, C, D, E, and IX and IY. But there were some things they left out, and this IYL and IYH is something they left out. Now, I should say they work for all this. This is what's known as undocumented opcodes, but the fact they're undocumented shouldn't scare you because they work on all Z80 systems. They even work on the TurboR's R800, which is a Z80 compatible. So this is something you want to try and use. What is it? Well, when we've discussed the indirect registers of IX and IY, well, these are 16-bit registers, and just like HL, a 16-bit register pair is a pair of other 8-bit registers, and IX is actually made up of IXH and IXL in the same way as HL is made up of H and L. So we can use the two parts that made up this 16-bit pair separately for our own purposes. And in the same way, you've got IY, and that has IYH and IYL. Now, the big advantage of this is this gives us some more registers to play with, and in this case, it's going to save us from using pushes and pops or from using temporary memory to store some values. The disadvantage is they're slow. If you look at the bytes they compile to more bytes than other registers would for the same command. So they're slower, but if it's a choice between that and pushing and popping or saving to temporary memory, they may be faster. So you just need to be quite careful when you're using them. But by all means use them. As I say, they're reliable, they work on all Z80s, and it's a good way of gaining some speed, because I believe back in the sort of 80s, the programmers often didn't know about these commands. So they're a way that we can gain advantage over the 80s programmers, and potentially why the games that are coming out today just look so much better than the games did back then and are faster. It's because people know more about how to tweak and how to push these systems, so they can gain those extra little bits of speed that make the frame rate better, that make the sprite routines faster, and that's what it's all about. So we're going to use it. We're going to use this undocumented opcode, and we can feel a bit clever that we're using something secret while we're doing it. So we're going to load into IYH, and then we're also going to load this into. We're going to store it in the array. Now this is actually our width, so because as I said, we're reading backwards, so we're loading the width in, and we're storing it in IYH, which is going to be our width loop counter, and we're also storing it in the destination memory. And this is so that when we put the sprite, we don't need to worry about how actually big it was, because it's quite hard to show a sprite at a different width and height than it originally was. So for simplicity, this sprite viewer won't do it. So store it in memory. That makes the basic code that we call this with a little bit simpler. And then we're going to do the same. And we need to do inc de, because we've used up that memory position. And then we're going to do the same, but this time we use IYL, and this time we load from IX plus 0, and that loads in the height. We're storing the height in IY, which is our loop counter for the height, and then we're storing that in memory, and then we're increasing DE again, because then once this has been done, we're going to start storing the actual byte data that made up the sprite. And so what we do now is we do call get screen pos. I'll just put my colon in there for a bit of professionalism. And then we've now got the screen location of the first line of the sprite that we're going to get from the screen. So we're going to create a loop called repeat y. We're going to push HL because we need the screen position for our get next line command needs the position of the start, so we're going to back it up so that we can get it back for our get next line command. And then what we're going to do is load B with 0, and then we're going to load C with IYH, which if you remember is the width. And then we're going to do LDIR, which is our load increment repeat command. If you're not familiar with it, you should be. It was in a previous lesson. But what it does is it loads from HL, which is the screen memory, writes to DE, which is the destination memory of our sprite, and it repeats for the value of BC, which we've just set to the width. So it's going to copy one line from the screen to the byte destination. Very easy. As I say, it's not the fastest way, but it's the fastest way I can teach you at the moment with what we've learned. So we'll carry on. And then what we're going to do is we're going to use our get next line command, which will just copy pasting to avoid typos, so it was a good thing. And that will update HL so that HL is now the next line in the screen memory that we are copying the sprite from. And then what we do is we do dec IYL using that undocumented register to as our y loop counter, and then we do JP NZ repeat y. So we're going to keep repeating until the y loop counter is 0, copying those lines to the destination memory. Now when it's done, we're going to do something a little bit cheeky. What we're going to do, we're going to delete these comments I put in for no reason. We're going to do load last sprite pos plus 2 minus 2 comma DE, and then we're going to return. Well, hey, what's all that, you're thinking? Where's this last sprite pos? We've not discussed that. Well, okay, we'll discuss it now. We did define a third command here called get mempos in our jump block up here. So let's create get mempos now. Now, what's this command do? Well, this is going to be run from BASIC again, and what it's going to do is it's going to allow us to give BASIC the memory position of the next sprite that we can grab to. So let's just make a start. We'll have a look at it exactly how it works later. So we're expecting one variable, and if we've not got one, we return. Now, this is something slightly odd. You'll see that when we call it with a variable name and an @ symbol beforehand. What's that mean? Well, when you put an @ symbol in BASIC, in Locomotive BASIC on the Amstrad CPC, rather than passing the number in that variable like it usually would, it actually passes the address of the variable in BASIC's memory. This would be called in some programming languages as pass by reference. It passes the address because that allows us to change the variable itself. The effect is that our assembly language code can find where BASIC has got its variable, change the variable, and then when BASIC uses the variable next, it will be the value that the assembly gave it. We're going to use that in this program to define a bank of memory for sprites. We're going to start filling that bank, and then we're going to use this command to say, hey, that sprite we just saved, well, where did it finish? Okay, well, that's the address of the next sprite. And then we can use those variables to show the sprites on screen. Rather than worrying about the memory addresses, we can just use integer variables as those memory addresses. It may sound a little bit confusing, but hopefully it'll become clear when you see it working. But anyway, so we need to load from the 16-bit variable we've just been given. So we load ix plus 0 into L because it's little endian. Everything's backwards, which always catches me out, as it nearly did. So we're loading HL. Now HL isn't int because of that @ symbol. What HL is the address of int. So now what we need to do is we need to load DE with a value. Well, what's that value? Well, it's just going to be 0. Why is it going to be 0? Because we're using self-modifying code. I love using self-modifying code, and you're not going to stop me. So what we're doing is we load in DE with a byte, with 2 bytes, and we're going to modify those bytes using this label here, because this label here, -2, will be the bytes that will be loaded into DE. You can confirm that if we do an assemble. Now here's the load DE, 000 command, and load DE is this byte 11 here, and these zeros are these zeros here. And here's the label last byte plus 2, and that's here. Now if we subtract 2 from that, that's those 2 bytes. The reason I've put +2 on the end here is just a reminder for me that when I want last byte plus, I need to subtract 2 to get the correct memory location. Which is why you've got this last byte plus +2 -2. And if I'd forgotten the -2, it would just look like that, and it would immediately tell me, hey, you're being stupid. This is not the correct memory address. It's the correct memory address +2. So there we go. Now, one thing, if you're not using WinApe, this way of specifying the label name is a bit odd. It has the colon at the front. A lot of them don't like it, but you could put it at the end and you could have it there. It will work just the same. I put it here just because it makes things a bit neater, and it reduces the line count, and it also makes it very clear that this is relating to this, whereas if it was on the next line it would just be a little more confusing. So you'll have to excuse me, that's the way I do it, and I'm not changing it. So what we need to do is we need to load the memory. As I said before, HL will be the memory address of the variable int. So we need to load the first byte of that memory address with E, and then we need to do inc HL. We have to do inc HL, not inc L, because we've got no assurances about how the data is aligned. So it could go over a 256 byte boundary. So we can't just inc L. And then what we do is we load HL, D. We've now loaded those 2 bytes into what we're assuming is a 16-bit integer here, and then we return. So that's our get mempos command. Well, here we go. So we can load a sprite into memory. We can work out where we just loaded that sprite to. But we do need to have something else. We need a put sprite command. And this is the final piece of the puzzle. This will show the sprite back onto the screen. And that's how we use it. Now, we saved the width and the height before, so when we're putting the sprite to the screen, we only need to specify the memory destination and the screen destination. So, there we go. So we need three variables passing to us. If we haven't got them, then something has gone disastrously wrong. So we'll load E from ix plus 4. So D again is our screen is our data position of the sprite, and then B is our X position, C is our Y position again. Now here we go. You remember we said that the width was being stored in the sprite data, so rather than ask the user, we're actually reading it from the memory destination, and we're storing it in IYH again. And then we're doing the same for IYL. Okay, well actually, let's save ourselves a little bit of work here. What we're doing next is very similar to what we did before, so let's just copy paste it. Save me some programming, and let's save me some debugging time if I make any mistakes. So we can't use the same label name, so we'll change this to repeat 2. Okay, now everything is pretty much the same. The only difference is here. Now if you remember, LDIR copies from HL to DE. Now HL is the screen memory and DE is the sprite memory. Now if we do LDIR here, it will overwrite the sprite memory, which is the opposite of what we want to do. What we want to do is we want to load from DE and write to HL, but there is no command that does that. So we're in a bit of a pickle, but there's a way around it. On the Z80, HL is kind of a special variable. It's got a lot more power than every other register has. But we do have a bit of a trick for if we want to do something that only HL can do with DE, we have a special command. And what it is exde, HL. What does this do? Well, it exchanges the value in DE with the value in HL, and it does it very, very fast. Now you may think, well, if you could do some kind of push popping, you could do push DE, push HL, pop DE, pop HL. You could do something like that and swap them like that. Well, you can do that if you want, but you know each of these is about 11 ticks. So yeah, you're going to use 40 ticks here. This is 4. This is very, very fast. This is the fastest way you can swap two variables going. And the reason it's so fast is it doesn't copy the data between the registers in the Z80. I believe it actually relabels the registers so the data never moves. Very, very fast. It's the fastest thing you'll get. So as I say, this allows us to use LDIR backwards so that in effect we are copying from HL to DE. Even though the LDIR command hasn't changed, we've swapped over DE and HL to reverse the effect it has, and that allows us to use it in that way. So there we go. Now let's compile, and let's give it a go. So let's write a little program. We're going to reset the screen to mode 1. Now this is important because if you scroll the screen, the memory addresses all kind of remap. So by using the mode 1 command, we're resetting everything to a known situation, and that's what we're relying on for this routine to work. So we'll just do that, and what we'll do now is we're going to do print AA11. Oh. Now, what are we doing here? Well, we're just putting some junk on the screen so that our sprite grabber has something to sort of to actually grab. If you were being artistic, you could load in a screen from the disk, or you could use a bunch of line commands to actually define something here. Now, we're going to define a variable called S1% here, and we're going to define that as 9,000. To excuse my very poor typing, I work a lot with foreign machines, Japanese, American, English, and also emulators, and I've completely forgotten where every key on the keyboard is and just end up fumbling around like an idiot most of the time. So sorry about that. You just have to get used to it. So we've defined a variable called S1%. Now the percent symbol says to BASIC, this is going to be a 16-bit integer. The reason we're doing that is we're going to pass these directly to our assembly code, and our assembly code only works with 16-bit integers. If you took the percent out, I think it would define it as a real number, which is quite complex because it has this exponent mantissa thing, and I don't know how it works in assembly, and I don't touch it. It'd be very slow for gaming, so it's not really relevant for games, so I don't worry about it. So really, all to take home from this is put your percentages in, otherwise this isn't going to work nicely. So we'll do call and 8,000, which is our get sprite routine, with S1% and 00624. Now, well, that's coordinate 00, so the top left-hand corner of the screen. 6 bytes wide, now 4 bytes per pixel, so that's 24 pixels wide, and 24 lines down. So it's a 24 by 24 sprite if you're counting in pixels. So then we will do 80 call and 8003 comma S1% comma 50 comma 50, and we'll run that. I don't think that worked, ladies and gentlemen. Just bear with me a moment while I figure out what went wrong. Okay, I think we've discovered the problem. The problem is I am an idiot. I have put ret, not ret, in Z. So that will work. I also realised I failed to explain something quite important earlier. The jump block, I said it started at 8,000 and it allowed us to know where the commands would be in memory. The important thing to know is that jump with any label at the end of it will always be 3 bytes. So you can be certain that this will be at and 8,000. This will be at and 8003. And this will be at and 8006. And if you look at my Chibiakumas code here, you'll see I've actually put them all here. So you can work out where each command is, and as long as you don't change the position of the commands in the jump block, you can know that every time you call an AND 8000 from a BASIC, from another assembly program, from whatever, you will get to this jump command, which will jump you to the get sprite command within the program, and nothing else needs to know where the get sprite command is in the program. It doesn't need to know that label definition. All it needs to know is that this jump block will be at 8000. So let's compile that. Let's run our program. Okay, well, because of that rather unfortunate crash, we've lost some code. But let's do a little trick here. Now, in case you haven't guessed, I've got all of the source code that I'm typing in today sort of written in off the screen. So here is the program that I had just typed in, and because of my rather unfortunate error, crashed the computer. Now, rather than type it in again, I'll show you a little trick. If you go to auto type here, and you paste in some code, and you click OK, you'll see it will start typing. But hey, that's slow. Well, Shift and F4 will fast forward, and Shift and F3 will slow you down again. So you can type in a ton of code here really, really quickly. And what I could have done, if you've crashed your machine, but it's still running to some extent, you know, it's stuck in an infinite loop, but you can't get back to basic. What you can do here is you create a new program, read basic, and WinApe will pull out the text that you just had in, and then you can copy paste that into that autotype function there. I've done it occasionally. I even got a basic text adventure online that was a snap save shape, loaded it up, machine immediately crashed, couldn't fix it, but I was able to grab the entire code and rebuild it. Unfortunately, you can't assemble this, so you do have to use that retype command, but it's got me out of holes, definitely worth knowing. Okay, unfortunately there's another little bug here. I put in 80, I should have put in 808 here. I apologise for that. Let's compile this. And there we go. That's the expected result. So we've debugged our code and we can now actually make a bit more of a start on the basic side of things. So let's see what we got so far. So this version's slightly further ahead than the pre-crash version. We've defined three integers, three 16-bit integers for our three sprites that we're going to define. But we've set the second and the third one to 0, and there's a good reason for that. So let's carry on with our code with line 60. What we're going to do is call and 8006, at s2%. Well, what's that? Well, if you remember, if we look at our jump block, 8006 is get mempos. That will call the get mempos, and it will pass by reference the s2 variable. Well, s2 is going to be sprite 2. And what it will do is it will get the last memory address used by sprite 1 and store it in sprite 2, so effectively being the start of sprite 2. This will allow us, when we put sprite 2, to use this variable as a reference for sprite 2's data. Let's carry on and we'll see that in action. So 70 will be, try and avoid any more bugs by just copy pasting this. So we're going to load in sprite 2. We're going to load it from X position 6, and it's going to be 6 wide and 24 tall again. So this is going to pull in the 1s, the 2s and 3s as a second sprite, and then 80 and then 75, sorry, we're going to run our 8006 again, and we're going to pull in sprite 0. Well, what's sprite 0? Well, sprite 0 is just going to be a little bit of a cheat. It's going to wipe the screen so that we can erase one of the sprites. This will be 70, line 78, poor numbering here. So we're going to load from 12, which there is nothing on screen at 12. So that 12 position will be basically just this bit here. And as I say, it's just a cheap way of clearing the screen. So that's how we can read sprites and define them. Now, I've got this whole little program that's going to be quite fun, but I'm not going to type it all in. So I am going to cheat. So we're going to use autotype, and we're going to type in the rest of the program. I will talk it through as it types. Let the computer do the work. So we're defining an X and Y coordinate, and we're backing them up. We're then reading a key from the keyboard, and what we're going to do is we're going to use ZX, K and M, I think it is, K and M, yep, and we're going to use those to move the sprite around the screen. And if the coordinates have changed, then we're going to re-show the sprite after erasing the old position by using that blank sprite we just created. Okay, now let's have a go. It didn't work. We've still got a bug. Okay, well, there was obviously a bug in my basic code there. Unfortunately, it's crashed, so I can't see it. Hopefully, by the time you see this, I will have put a comment on screen pointing out what an idiot I am and where I went wrong. But here's what it should have done. As I say, it wasn't a bug in the assembly code. So I'm now pressing Z and it's moving left. I'm pressing X and it's moving right. K up and it goes up. M and it goes down, and you did just see the rather serious flaw with this program. It has no ability to clip, and it's not even checking if the sprite goes off the screen. So if I go up, all kinds of crazy stuff, and yes, the machine has crashed, which is what will happen because it's probably overwritten part of the firmware memory. So, okay, little program there. It's really just a skeleton for a program, to be honest. I just wanted to show you, firstly, how to test today's tutorial, but also something like this should be enough for you as a beginner to write your own little game. Maybe you could write a sort of Pong game or some kind of shooter where there's two players trying to shoot each other, or something like that, something with a few sprites on screen, a bit of keyboard input. This should be enough to get you started, and you've got the power of that assembly language giving you those fast sprites, and not just giving you fast sprites, but it's a program you've written yourself. You can tweak it, you can make it better, you can fully understand it. Now, back in the 80s, I had these kind of sprite routines that I'd just done as type-ins. The problem I always had with them is things like the org statements were all encoded in the code. So I knew how to load them into memory and how to work them, but then I'd have a music program I wanted to use as well, and they'd use the same memory, they'd crash, and I didn't have a clue what to do about it. I was always stuck like this. It drove me up the wall. I always had great music programs, great sprite programs, great text effect programs. Could never use them together, completely useless. And that's why it's so great to be able to go into assembly language, to write these little programs yourself. And okay, this isn't the best sprite routine in the world by far, but you've made it yourself. You know how everything works in it, hopefully. And that means if it doesn't work, you can fix it. And that's really the key of this kind of thing. Okay, so there's just one more thing I want to cover today, and it's really it's not relating to the sprite example. It's just a sort of extension of the concept of the lookup table. We use the lookup table for our memory addresses here, but there is another quite exciting use for it that it's definitely worth you knowing at this point, and that's called a vector table. So I'm just going to add this to our jump block at 8009. And it's a totally separate program. So let's go to the bottom here. Now, I think I'm going to have enough trouble editing this video already with all the mistakes I've made. So let's save myself a little bit of time, and we're going to create these three test programs here. These test routines, sorry, that just print an A, a B and a C on screen. And they use the print char command that we looked at before. So that's all they do. And now what this vector table test command is going to do is it's going to take just one variable from basic, and if it doesn't get it, it's going to return. And how does it work? Well, it's going to take a value from 0 to 2, and depending on the value it's given, it's going to run one of three commands, and it's going to do that using a table. And here's the table it's going to use. So if it's passed to 0, it's going to run test A. If it's passed to 1, it's going to run test B. And if it's passed to 2, it's going to run test C. And this is basically the same as our lookup table here, where this was line 1, this was line 2, this was line 3, and this was line 200. So the concept's very much the same. We're just going to load in 2 bytes, and we're going to use them as the destination for a jump. Well, okay, let's make a start. So the first thing, in the same way as before, is we're going to load HL with the vector table address, which is the address of our lookup table. And then what we want to do is we want to load B with 0, and we want to load C with A. Now A is our command, but wait, there's something we need to do. We need to double A, because these are these are actually what's called words. DEF-W stands for define word, and a word in 8-bit mathematics is 2 bytes. So it's defining 2 bytes. I'm not a big fan of the word word, it's very confusing, but it's a pair of bytes, and that's because addresses in 8-bit assembly are 2 bytes. So this label is a 2-byte label, and each line in this needs 2 bytes. So before we set C to A, we need it to double A. Now we could do add A, and that would work fine. But there's another thing we can do, and this is something I mentioned in a previous lesson, which is with relating to bit shifting. If we shift all of the bits left, we effectively double A. So let's make a use of it. It's a great example. You always want to do things in the simplest way possible, and when you want to double things, bit shifting is the fastest way. Now, I should point out we're shifting an 8-bit register, so this command will only work up to if A is 120 up below 128 before the start of this command. Because if it isn't, if it was 129 when it doubled, it wouldn't fit in a single byte register, and that's why we didn't do that here. Here we added BC twice. BC is a 16-bit register, and the reason we did that is because if the line was 200, then doubling an 8-bit register would have caused a disaster, so we didn't do that. But here we can, because we're using a lookup table of just 3 values, so there's no reason not to. So we're loading BC with that, and then we load HL, BC. And now we've got the address of the command that the user has specified. So what we do is we load A with HL, we inc HL, and then we load H with HL, and then we load L with A. I should say I really struggled with this command when I started doing these jump tables, these vector lookups and things. Just feel free to copy this, just copy it verbatim. It looked very weird the first time I saw it, but it's just that's how you get something from HL into HL. So just use it exactly as it is here, and don't worry about it if you don't understand it. It makes no difference. Now we're going to use a special command here, which is jump HL, and HL is in brackets, so we're jumping to the address in HL. There aren't many of these kind of commands, but another thing you could, if you'd needed to do DE as we discussed before, you can push DE and then do a return, which is a kind of cheating way of having the same effect. But anyway, we've got this special jump HL command, so let's use it. Well, let's assemble this. Dear me, I've not done very well at all there. Add HL, BC. A few bugs today, sorry about that. So I've had to make a few corrections. Firstly, this should have been vector table test. And down here, this should have been vector table test. And I forgot the command to load in A from the user pass parameter. Very bad there, I apologise. So let's compile it. And now you can see we can pass 2, 1, or 0. Now, the important thing to notice is that the value in A, by this code, the value in A has been converted to a jump to the relative number of the line in this vector table here. Now, you're probably thinking, well, what's the advantage of this? Why would I want to do this? Well, there'll be times where you may need, like if I use my Chibiakumas game as an example, there's times where a value in a number in data, like the movement of the enemy, for example, may be the low nibble of that might be converted by a lookup table of 16 possible movements, and this kind of code is used to make the jump to one of those 16 possible movements. And the other thing to sort of bear in mind is you could equally have done this with CP0 jump test A, and then CP1 test B, and CP2 test C. Well, that's another way of jumping to things, and also you've got the jump block at the top. But, well, how much memory does each of these possible options use? Well, the vector table here, if you ignore this sort of shared code here, the vector table is using 2 bytes for each label. These are using 3 bytes for the jump and 2 bytes for the compare. So each entry here is 5 bytes. And the jump block, which is a far more restrictive option, even that's 3 bytes. So actually, the vector table is the most memory efficient way of allowing you to do a jump to one of multiple predefined positions. And so with my Chibiakumas game, what I'm now having to do, because the jump block has become so huge, I've had to stop adding entries to the jump block simply because I can't afford that 3rd byte that the jump block is taking up, and I'm using vector tables that only use 2 bytes. because things are now so tight that that 1 byte difference is worth saving. So the vector table is great for jumps based on data, because you can define different numbers to mean different commands. It's great for saving memory over a jump block, and it's certainly great compared to a huge compare block like this, because as I say, each entry in this is 5 bytes, each entry in this is 2, and that saves you a ton of memory very quickly. And also, if you were going crazy on this and you were comparing down to 255, well, not only is it going to take a lot of memory, but the processor is having to tick down each one of these, so it would have to tick down 254 incorrect entries before it got to the 255th one that would actually be executed, whereas this vector jump is the same amount of code executed every time, so it's not just smaller, it's actually faster. So yes, a great reason to use vector tables there. But jumping aside, memory lookups aside, this concept of using tables of data and converting numbers to relative locations in that table for reading data is essential for all kinds of things in game coding, because there's going to be so many times you need to do those kind of conversions, especially because your data is always going to be so limited. As I've said before, the bullets in Chibiakumas, there's only 3 bytes defining the position and movement of every bullet in the game, because there's just not enough memory to spare anymore. And even the enemies are only using 8 bytes for every possible attribute, including their sprite, their animation, their movement, their life. So you're often having to simplify things all the way down, and by using lookup tables you can convert a very small thing like a nibble or 2 bits into a more complex set of attributes, or allowing that to call an execution of a movement pattern, whatever you need. So something that's very worth considering, and definitely worth you knowing at this point. So okay, I think we're pretty much done today. I apologise for a few bugs today. These examples are getting bigger, and I'm afraid I'm not the most skilled typer or programmer even, so you'll have to bear with a few little bugs here and there. But hopefully what you've seen is interesting today. You can download all of the source code, including the basic example for today's lesson. If you download my sources file off my website, you will see there is a disk image, and that disk image does have the source code to the lessons that have basic programs attached to them. So please download that, give it all a go, and if you want, please make your own little basic programs with today's sprite routines to give them a little bit more visual appeal. So thanks a lot. Please follow me if you want to see more. I'm planning to do some more of these basic Z80 tutorials. We've got a few commands in Z80 left to learn. Once we've finished with that, I'm hoping to move on to more advanced things, recap lessons where I go over the things I've possibly rushed so far, and also I'm going to start with the true thing of using code fragments from my game. I'm going to break them down, make them simple, and I'm going to give them to you so you can use them to write your own games for multiple systems without writing your own disk routines, without writing your own sprite routines, and you can get started really quickly. Once these basic lessons are finished, I'm also going to do some recap lessons, because some of the stuff here I know I'm covering very, very fast. I didn't want this course to be a series of 5,000 episodes that would teach you each command in crazy amounts of detail. I wanted it to be something where you could get in really, really fast and feel you'd at least had a taster for each of the commands. Even if you didn't necessarily feel confident with them, at least you'd seen them, at least you'd seen a usage of them. But then if people need it, if people feel it's appropriate, I will go back and I will cover each of these commands in more detail. I'm perfectly happy to do an entire lesson on the undocumented registers if that's what people want to see. But yes, please follow me. Please let me know what you think. Thanks for watching today, and goodbye.